Okay, well, I'm going to pick up where I left off on the last lecture notes, and I'm going to talk about electron configuration. Now, I realized I didn't do any practice with the last set, so I'm going to start off doing practice for electron configuration. So we're going to write the electron configurations for each of these, and then I'm going to talk about how to do shorthand electron configuration notation, more shorthand than what we're about to do. So this will actually help kind of prove a point. So what we're definitely going to need is a periodic table. Mostly what we need to know is we need to know how many electrons each of these have. Because remember, the electron configuration is going to be the same no matter what. Now, you probably want to get out in front of you, you want to get that list of the order of the subshells. Now, again, don't worry about memorizing it. So just get it out, look at it for now, or go back to my slides and write it down. In fact, as a review, let me go to it. So here's the filling order. I'd recommend pausing it and writing these down so we can do the next part. So here we go. Mostly what we need to know is we need to know how many electrons are in nitrogen. So just neutral nitrogen, there are 7 electrons. I know this by looking on the periodic table and seeing that it is element number 7. Aluminum, having an atomic number 13, must have 13 protons, and if it's neutral, must therefore have 13 electrons. With rubidium, must be 37, and sulfur must be 16. So here's what we're going to do. We're going to start out, and all I have to do is fill in the subshells in order until I run out of electrons. So for nitrogen, I only have 7. 1s2 is 2, 2s2 is 4. Now I can put 6 more into p, right? Because p's have 3 orbitals in them and can hold up to 6 electrons. But I don't have 10 total electrons, I have 7, so it's going to be 2p3. Easy enough. Aluminum has 13. 1s2, 2s2, 2p6 for 10, 3s2 for 12, and then only 1 more, 3p1. Right? Rubidium has 37. Now this one's trickier. We're going to start straying into those orbitals where they get out of order. 1s2, 2s2, 2p6 for 10, 3s2, 3p6. That's only 16. We're not even close yet. Oh, I went out of order, didn't I? No, I didn't. I'm fine. 4s2. So that's 18 now, right? 6 and 6 is 12, 13, 14, 15, 16, 17, 18, 19, 20. I guess I miscounted. Looks like we're at 20 now. Yes, 20. So now, 3D, we can put 10 more in there. And that's 10. So now we have 30. Next comes 4p. 6 will give me 36. I've only got 1 more electron to put in. 5s1. Next, sulfur. 1s2, 2s2, 2p6 for 10. 3s2 for 12. 3p4 for 16. Okay, now, I will teach you a way to do this quicker. But for the moment, let's talk about how to write this differently. Something that's really important when you're looking at all these, notice that it goes in the same order, right? We're going in the same order. And the only thing that really distinguishes the electron configuration of one atom from another, or one element from another, is where you stop, right? The only thing that really matters is where you stop. So, for reasons I'm going to talk about in a little bit, what we're going to do is we're going to try to just focus on the last shell. So do you guys remember what a shell is? A shell is that broadest category, and it's represented by N. So any subshell that has a 1 in front of it is in the first shell, and there's only one subshell, S. 2, so this number out in front refers to the shell, right? 3, 4. So what we're going to do is we're going to start representing elements by what they look like in their last shell. So as you notice, some of these get really, really cumbersome. Like 10 has just this really obnoxious electron configuration. And it's obnoxious for no good reason, because we know that the order is always going to be the same. It just matters where I stop. All that's really important is that I'm going to end in 5p2. There's a little bit more that's important. But even if we focus, so remember, each of these, so 5p, 4d, each of these is a subshell, and in them are a number of orbitals. But the last shell involves the 5s and the 5p. So what we're going to do is we're going to use symbols to represent them. Now, what we're going to do is we're going to use the symbols of the previous noble gas to represent some of the electrons. So in the case of 10, if you look on the periodic table, now when I say previous noble gas, so 10, let me get out a periodic table. If you look, 10 is closest to the noble, so remember these are noble gases. It's closest to the noble gas, xenon, but we can't go to the next one with more electrons, right? We can't do, 10 has the same electron configuration as xenon, but minus some electrons. We can't do that. We have to go back to the previous one. So the previous, we go back, we have to go all the way back to 36, krypton. So what we're going to do is we're going to use krypton to represent it. We're going to say, and there's a reason we use the noble gases, and it will become clear in a little bit, but we only use noble gases for this. Only ever use noble gases for this notation. In fact, often it is called noble gas notation. So what I'm going to do is I'm going to say the electron configuration of tin is actually krypton. Wait, not krypton. Yes, krypton. What am I talking about? Krypton, which has the first, right? Krypton has atomic number 36. So that we don't need to include the first 36 electrons, right? So 2, 4, 10, 12, 18, 20, 30, 36. Right? So all I'm going to do is I'm going to write krypton and then all the electrons that tin has, because this is actually the electron configuration for tin, all the electrons that tin has that krypton doesn't. Now, something that's interesting, if we look at the noble gases, so looking at the electron configuration of tin, or krypton, we get this. This is what I said. All right. Looking at the electron configurations for the noble gases, if we look at helium, helium's the odd duck, so I'm going to get it out of the way. Helium's electron configuration, and I don't want to write it like that. I want to write helium, its electron configuration is just 1s2. And you'll see some similarities here. Neon is 1s2, 2s2, 2p6. Argon is 1s2, 2s2, 2p6, 3s2, 3p6. Krypton, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, wait, yep, 4s2, 3d10, 4p6. I'm going to have to back up xenon a little bit. Xenon, this is the last one I'll do. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. There we go. So, what do you notice in common about all the electron configurations of the noble gases? There's, ignoring helium, right, you'll see a pattern. They end after p6, right, after filling the p subshell. So, there's also something to keep in mind for later. With the exception of helium again, you'll notice that all of the noble gases end in a similar way, p6, right? But Now we have neon goes 2p6, 3p6, 4p6, 5p6, and actually this number before the p6 that they end on correlates to the row number. So the number, so in row number 1, so in row number 2, neon ends on 2p6, argon ends on 3p6 in row 3, 4p6, 5p6, 6p6. Now, there is a way to sort of make a general statement that also includes helium. Just take a moment, pause, and look and see if you see a pattern. Okay, hopefully you've started it again because you've either given up or you figured it out. And the pattern that I'm talking about is, even if you want to include helium, you could say, instead of saying it ends on p6, the electron configuration of the noble gases all end just before you would need to start a whole new shell, right? Now, I'm not going to say they have a full shell, because in the case of argon, there's 10 more electrons that are going to go into 10 later, but this represents the point before we have to start the 4th shell, right? And that is really significant about noble gases. That's what makes them special. But this is also how you can know where in the configuration they would start. So let me show you kind of how to do electron configuration from what we know so far. So let's do the noble gas notation electron configuration for the following atoms. So give these a try, and then come back. So barium, now I'm gonna hope you're looking at a periodic table, because I'm looking at one, and I think it'll be troubling if I keep going back and forth. Barium is, fine, I'll actually go back and forth. Barium is here, right? So the noble gas that we're going to look at is, we're going to use xenon, right? Now it's important that xenon has 54 electrons, barium only has 2 more, right? So using that order that we've talked about, right, we know that barium, we're just going to have xenon here, Xe, right? And that takes care of the first 54 electrons. Now, looking at the periodic table, we know that xenon is going to end at, so this is row 1, 2, 3, 4, 5. It's going to end at 5p6. So all we have to do is look up what the next thing is, and by that order, it's 6s. Now, barium only has 2 electrons that xenon doesn't. So 6s2 gets us our 55th and 56th electrons, right? Let's do something similar with iodine. If we look at iodine, iodine's here. Now, it's really tempting to just go here to xenon, but I can't. I have to go back to the previous one, so krypton. So krypton has 36 electrons. Iodine has 53. And that is going to be a difference of, trying to do mental math because I'm very bad at it, so it looks like it's going to be 17, I think? Yeah, 17. The difference of 17 electrons. And so what we're going to do is we're going to look, and krypton is going to end with, 1, 2, 3, 4p6. So the next one is going to be 5s, right, by that order that we've done. I don't, again, not expecting you to memorize anything. Oops, that's not what I wanted. Still not what I wanted. Easier this way. There we go. So what we're going to do is I'm going to start with iodine. For iodine, I'm going to start with krypton, because I have to use a noble gas, and it's the previous noble gas, with its 36 electrons. So remember, krypton, being in row 4, is going to end on 4p6, so we start on 5s2. Then comes 4d10. Right, we're trying to expand the remaining 17 electrons that iodine has. It has 53, that krypton doesn't with its 36. So 53 minus 36 is 17. So I've got 12 of them now. So 17, I need 5 more. 5p5, right? It also makes sense because iodine is 1 short of being xenon, which would end on 5p6. So it makes sense that it's going to end on 5p5. And you're going to see a lot of the stuff come back. So iron, right? Let's take a look. Iron is here at element 26, and its previous noble gas is argon with 18. So we've got what looks like 8 extra electrons that iron has that argon doesn't. Argon's going to end on 3p6, so let's go forward. So iron is going to be argon 4s2 3d. Now remember I said we've only got 8 electrons, right? So 3d6, right? So 8 electrons that iron has that argon doesn't. That's how I know how many to put. So hopefully you're seeing how I know how many to add after the noble gas, right? It's just the difference between the number of electrons the noble gas I'm using has and the element I want to show. Also, I know where to start because I know the noble gases, with the exception of helium, are all going to end after a P6, and we're going to start with an S. I guess maybe that's another way to say it, is that after a noble gas, you're always going to start with an S, and it's going to be the S of the next row. So if argon is in row 3, after argon's always going to come 4s. After krypton being in row 4 is always going to come 5s. And after xenon being in row 5 is always going to come 6s. Right? So it's always the next row and then starting with s every time. There's no exception there. Noble gas. So even if we want to talk about helium, if you're using helium, the next one's going to be, because helium's in row 1, it's going to be 2s. Is where you're always going to start. Okay, so that's enough about electron configuration, or not just the noble gas electron configuration. So that's that shorthand.